Hello, welcome to the very last part of BC Calc. Okay, here we go. Let's talk about finding the area inside a polar curve. So, when we talked about areas enclosed by curves that were given in Cartesian coordinates, we always had to give all these boundaries, right? So from here to here, x-axis is a boundary, y-axis is a boundary. They would give you an upper boundary or a lower boundary, or sometimes they would say enclosed by these two curves, and then there was a clear upper-lower boundary, and there were endpoints, the intersection points. With polars, a lot of times they can say find the area inside this curve, because as we know with polar graphs, they're those kind of loop-de-loop graphs, right? So a lot of times you have like a loop, and they'll call it one petal or one leaf or whatever. So the key to finding the areas inside of these functions is really finding the limits of integration, right? Figuring out what values of theta are going to plot the part of the curve that we need. Okay, so that's what we're going to focus on a little bit here. The actual way to find the area inside a polar curve is really, really, really straightforward. I'm going to give you the formula. You've got to memorize it. Okay? Anytime you want to find the area inside of a polar curve, let's hope my computer operates and doesn't embarrass me here. If you want to find the area inside of a polar curve, here's your formula. It is literally just 1/2 times your r squared. So you'll be given an r equation, right? R in terms of theta. You take it, you square it, you multiply it by 1/2. And in fact, I always pull the 1/2 out front, so it's not even in the integral. All you then have to do is figure out what your limits of integration are. Now these look really fancy, right? Alpha and beta. It's just from a to b, except since we're talking about thetas, they tend to use alphas and betas, right? But these are going to be your limits of integration. It'll be like from 0 to pi, or from pi to pi over 2, or something like that. But this is literally all we're going to do. We're going to take our r, square it, multiply it by 1/2, figure out our limits of integration. It's very, very, very straightforward finding the area inside of a polar curve. Again, memorize that formula. Memorize it. Okay. The hardest part of these is finding the limits of integration. Okay, now, good news. These problems are always calculator problems. So, worst case scenario, you can play around with your calculator and figure out, like, hit trace, right? And figure out the limits of integration. But I have found that if you just plot a couple key points, you can pretty much figure them out. All right, so let's take a look at one. Okay, let's see. Blending head. All right, we want to find the area inside enclosed by this curve. R is 2 times 1 plus cosine theta. So here's my curve. It's called a cardioid because it looks like a heart. Okay, so I know that my equation for my integral, I know my integral is going to be 1/2 times this thing squared. And I can even simplify that a little bit. This will be a 4 and this will be a 1/2. So I can pull a 2 out front and then just have a 1 plus cosine theta squared in here. Now I'm doing that because I'm going to have to put this into my calculator, right? So I don't want to have to enter all this if I don't have to. So now all I'm going to have to do is put this into my calculator, and then in the end I can multiply it by 2. All right, so I just have to figure out what my upper and lower limits of integration are. In other words, from from theta equals what to what, it's going to sketch out this whole curve. So here's what I do. I make myself a little tiny table of values over here. Right? And I am literally just going to put in the least interesting values for theta ever and follow this curve, kind of like it's a parametric. Okay, so when I put theta of 0 in to this function, when theta is 0, the cosine then is going to be 1, so this becomes 2 times 2, or 4. Okay, so theta is 0, r is 4. That's this point right here. At pi over 2, your cosine is going to be 0, so this will be a 2. So look, At pi over 2, I'm at 2. So I go like this. So if I start at 0, if my lower limit is 0, if I go from 0 to pi over 2, that gets me to here. It's only this part. Okay, I'm still missing this part, this part, and this part. So let's keep going. When I put in pi, you put in pi, you get cosine is -1, so this thing comes out to 0. Look where that puts me. When I'm at pi, my radius is 0. That puts me right here. Okay, so if I go from 0 to pi, that's going to bring me to here. So actually, great news, I could just make this go from 0 to pi and then double my integral. Right? That would do it, because that would give me, from 0 to pi gives me this top part. So I could do that. Just multiply by 2, right? Or if you keep going, you find out that 3 pi of 2 puts you down here, and then 2 pi brings you back here. So you could also just take out, nix the 2, go from 0 to 2 pi. Completely up to you. Okay. But again, you can see how just plotting a few, just plotting a few points kind of helps you figure out what theta values you need to sketch out your curve. All right. So if I put this into my calculator, interestingly, I get exactly 6 pi. Right? So this area all comes out to 6 pi. Now, something really interesting about polar curves is you may have noticed there's no above and below cancellation type thing, right? Because it's not an above and below, it's an around. So we don't get cancellation with polar curves the way we got cancellation in Cartesian coordinates, which is kind of interesting. Okay, so that's inside a curve, right? So any curve they give you, again, if you just make a quick kind of plot a few points and figure out what theta values you need to sketch out the curve. One of the things you can do in your calculator is if you put it in polar mode, and we can mess around with this in class, if you put it in polar mode and you go into your window, it asks you what theta values you want, but it also asks you for your theta step, if you will. And if you make the theta step really small, when you watch the graph, it graphs really slowly, and it helps you to see as the theta values go where it's taking you. But you can also play around with, okay, well, what if I went from 0 to pi, and then it would only graph that upper part. And then if you graphed from 0 to 2 pi, it would show you, it would graph the whole thing. So you can play around with it on your calculator a little bit. And again, you don't want to spend a ton of time playing around on your calculator, but it is nice that we always have our calculator for polars, so we can always mess around with it if we need to. And not that you would ever need your calculator to know what like the sine and cosines of angles are. Nobody needs that. Okay, so that's the area inside one single curve. The other way they can throw this at us is to ask us for the area between two polar curves. So if you can imagine here, I could ask you for the area inside the screen curve. That would be all this area from here. Ooh, look at that. From here out, right? That's all of this. I could ask you for the area just inside this red curve, right? That would be all of this area. What they're going to ask you for is this area in here, right? The area between these two curves. Now, when you think about this, I want you to think about the Cartesians and how we did it, right? If you wanted the area in Cartesians between two curves, it was always upper boundary minus lower boundary, right? So if this was f of x and this was g of x, it was just f of x minus g of x. Okay. It's going to be the same thing here, except remember, it's not an up and down, it's an around, right? So instead of saying upper minus lower, it's an outer minus inner. Okay. So let me just, if I can just possibly erase this. Okay, so let's think about just one tiny kind of slice of this area. Let's think about the slice from, if I wanted to find just this little tiny slice here. I'm always measuring from the origin, right? It's always an out from the origin. How far from the origin are you? So If I want to get this area right here, I need to know two things. What's my outer boundary? That would be your green curve. We call it big R. You know what this reminds me of? The washer method. The outer minus inner type of thing. And then I need my inner boundary, which we're going to call little r. Now think about it. If I do 1/2 big R squared minus 1/2 little r squared, that's going to be all of this area, 1/2 big R squared, minus 1/2 little r squared. That'll leave me with the area in between. It's very much like a washer, right? Where you take the whole cylinder and subtract out the hole in the middle, the empty piece. So take a look at this formula. It's exactly what we just said, only the 1/2 is factored out, right? This is 1/2 outer radius squared minus 1/2 inner radius squared. All they did was factor the 1/2 out. I'm going to say it now, like I said during washers. Do not do this. It's not the same thing. It's outer radius squared minus inner radius squared. If you do this, that requires foiling. That is r squared minus 2r minus little r squared. That's a no-no. You don't want to do that. You square and then you subtract. Order of operations is key here. Okay, so again, we're going to have to mess around with limits of integration here, right? Points of intersection. So if I wanted this particular area between these two, it looks like we're starting at 0 and then going up to pi. Or, I'm sorry, pi over 2. Sometimes they'll be nice and give it to us. Sometimes we have to figure it out. All right, let's take a look at a couple examples. Okay, let's take a look at one. It says find the area that lies inside the circle and outside the cardioid. So in this picture, one of the things that you may run into is if they give you two polar curves, sometimes if you're not so great with polar curves, you might not know which curve is which. Again, you're always going to have your calculator with you, so worst case scenario, if you can't figure it out, you can always just go to your calculator, graph them, and check it out. In this case, they gave us r as 1, and we know that that's the circle because it's just a constant value. And then that makes the other one the cardioid. Okay, so look, I need an outer versus inner instead of an upper minus lower type situation. So the first thing I've got to do though is figure out what the heck area they're even talking about. So again, I need inside the circle, so it's got to be within this red circle, but I don't want to be inside the cardioid. So this area over here is inside both of them. Think like Venn diagram, right? It's inside both of these. The area that's in the circle but not the cardioid is this shape over here, which kind of reminds me of like Man on the Moon type thing. It's like a crescent moon with a nose. All right, so that's the area I need. Now, you can see, and we can test the values here, right? But you can see this area looks like it goes from 3 pi over 2 up to pi over 2, right? I am inclined to say, well, let's go from 0, right? At theta equals 0, theta equals 0, the circle will be at 1, yes, and the cardioid will be at 0, and that's what's going on here, right? And then if you take that up to theta equals pi over 2, that's going to bring you up here to where they both meet at 1, right? So I'm thinking let's take our integral from 0 to pi over 2, and then we'll just double that, right? Because from 0 to pi over 2 is going to give me all of this. And then I know it's going to be double that. All right, so I need 1/2 outer radius squared minus 1/2 inner radius squared. So 1/2 big R squared minus 1/2 little r squared. Just got to figure out which one's which. Okay, so when I am looking at this area, and I feel like this one can be a little hard to see because it's just kind of a little bit hard to draw the arrows. If I'm looking anywhere in here, if I come from the origin to the outer part of my area, what I'm hitting is the circle, right? The circle is always the outer edge of the area. So my radius of 1, my r equals 1, that's the graph of the circle. That's my outer radius. The inside of this area, the kind of inner boundary, the boundary that's closer to the origin, is going to be my cardioid here, right? So outer boundary circle, and then this is my inner boundary. So my little r is going to be 1 minus cosine theta. Okay. At this point, it's literally a matter of putting it in the calculator, right? So I'm going to factor this 1/2 out so that it can go ahead and cancel with that 2. And then I won't have any numbers to deal with. So I have a 2 out front. I'm pulling out the 1/2 so that those can cancel. And then I have my outer radius, which is 1 squared, minus my inner radius, 1 minus cosine theta squared. And all I have to do is put that in my calculator. That's it. Now, you could do a little bit of algebra with this. Like you could FOIL this out if you want to, or you could just type it right in as you do. If you type it right in there just like that, you should get 2 minus pi over 4 if you do it by hand, or the decimal that you will get, which you will obviously have because you have your calculator, and you would never do a definite integral by hand on the AP if you have your calculator. That'd be crazy. You should get 1.2146. Now, just as a reminder, AP wants 3 decimal places, right? So you can either truncate and return 1.214. You can round and return 1.215. They will take both of those answers. You can write 1.2146. That's okay too, because all they're going to do is look at the first 3 and ignore the last one you wrote. But what you can't do is write 1.21. You could do everything right. You write 1.21 for your answer, you're not going to get the answer point. So at least 3 decimal places. Don't round before 3 decimal places. Okay, so I want to take a look at this same graph, but a different area in the graph, and see how that changes things. Okay, so same graph, except now I want to be outside the circle, but inside the cardioid. So I want the part of this graph that's inside the cardioid, but not inside the circle. So that brings me to this kind of moon shape over here. Okay, and again, notice I've got an outer boundary and an inner boundary, but this time it has switched. My outer boundary is the cardioid. My inner boundary is the circle. My limits of integration are going to switch here as well. So I know I'm going to have 1/2 my big R squared minus 1/2 little r squared, right? And we said that big R is going to be the cardioid, and the little r is going to be 1. It's going to kind of flip-flop it. So let's figure out some limits of integration. It looks to me they come together right here at pi over 2, right? So at pi over 2, the circle should be at 1, check. The cardioid should be at 1, right? So that's that point right there. That seems like a good place to start, right? Pi over 2. Now let's follow it. If we go to pi, circle's still at 1, but this guy now is going to be at 2, or because the cosine of pi is -1. So now notice, you might be saying, lady, that's -2, right? True, but this point on the graph is r of -2 theta of pi, right? So in other words, r of 2. So they're saying go out 2 and then rotate around pi degrees. So where you land is -2, but remember this number right here is the distance from 0. So because it's pi, it's putting us back here in this position. So don't let that little negative position there confuse you, right? So if I went from pi over 2 to pi, that's going to give me this upper part of my crescent moon. So again, I've got some symmetry here. I'm just going to do that and double it. I can, if I want to, go from pi over 2 down to 3 pi over 2. You can do that, right? You're not going to get any cancellation. But I don't know why. I like to use the symmetry. Okay, so again, let's factor out this 1/2, right? So if I factor out that 1/2, it'll cancel with my 2. I'm going to have a pi over 2 to pi. outer radius squared, so 1 minus cosine theta squared minus 1 squared d theta. And all you gotta do is pop that into your calculator. It's all about the setup here with polars. If you put that in your calculator, you should get 2.7854. Again, here AP would only accept 2.785 because there would never be rounding up at the 4. So your answer here would have to be 2.785. You can write the 4 if you'd like. Obviously, you don't need to. Okay, so that's area in and between, right? I don't know why. I just feel like I want to show you this. Something, I just think it's really neat. So we know that we could find the area of this circle, right, with pi r squared. Obviously, we know that. So the area of this circle, that red circle right there, is pi times 1 squared, also known as pi. And just in case you like making things difficult, we can use polars, our formula for the area inside a polar curve, to find that same fact, right? So watch. If I want the area inside that circle, the area is going to be, we know that this circle is created by going a full rotation around, so it'll be from 0 to 2 pi of 1/2 my radius squared. It's like, what? How is that going to turn out to be pi? Ha ha. This turned out to be 1/2 theta, right? If you integrate, oh, there's a d theta here, right? So that's evaluated from 0 to 2 pi. So look, 1/2 times 2 pi minus 1/2 times 0. And don't you really just come out with pi? Can you think of a more fun way to find the area of a circle of radius 1? I can't. It's almost as fun as finding the area of a rectangle using an integral. All right, so one more thing we got to do with polars. Just in case they ask. I'm hoping they will. Just in case. Okay. There's this formula for, we have the formula for the length of a Cartesian, we have the formula for the length of a parametric. This is how it turns out for a polar, right? So they could ask you for like the perimeter, where you could get wild and find the circumference of a circle like this, right? So notice here, it's r squared and then dr d theta squared. So if they give you r, all you have to do is take its derivative, pop it into this formula. It's really straightforward. Again, this is just kind of a one that you have to memorize. Chances of you getting the length of a polar curve are probably pretty low, but if I don't tell you about it, it'll be an open-ended, because that's how my life works. Okay, so find the length of the polar curve on this interval. Now look how nice they are. They gave us the interval. They didn't really need to. We could have figured out that it was 0 to 2 pi all the way around, but it's fine. Okay, so if I want the length of a polar curve, 0 to 2 pi, square root of, this long square root, r squared, so 1 minus cosine theta, quantity squared, plus the derivative of this squared. So dr d theta is just going to be sine of theta. So I have sine theta squared. Now, you can pop that into your calculator right as is, or you can do a little bit of algebra and save yourself some typing, right? If I FOIL this out, that's 1 minus 2 cosine theta plus cosine squared theta, and then plus sine squared theta. So you have this, which is a 1, and you just end up with, where am I going to put it? The square root of 2 minus 2 cosine theta, which is a little easier to type into your calculator. Completely up to you. If you want to do a little bit of algebra to make the typing easier, or just go for the typing. Completely up to you. Fun. Guess what this comes out to? All this hot mess comes out to exactly 8. So if I took this polar curve and I found its distance around the outside, its perimeter, it would be exactly 8. Pretty fun, huh? Okay. All right. So that is it for BC Calc. I have nothing else for you. Nothing else to teach you. Congratulations. So we'll work on some of these problems in class. We'll look at some polars, some parametrics, kind of get our arms around those, and then it's off to the AP we go. Any questions you have, pop them in the end of the video, and I will see you soon.